Hello, everyone. Can everyone hear me all right? Cool. So my name's Noah Gordon. Noah Z. Gordon on Twitter, GitHub, Slack, everything. Please don't confuse me with the other Noah, Noah Hall, who's contributed a lot more to the Elm community than I have. And also, please don't confuse me with the gentleman who spoke before lunch, who copied my outfit. We came down from the hotel, and we were like, well, someone has to change. But neither of us did. So I'm going to give a talk called Cooking with Elm, How Lasagna Taught Me the Meaning of Types. This is about a somewhat different application of Elm than building web apps, which is what it's marketed to do. I used Elm to build a DSL for cooking recipes, so I'm going to talk a little bit about that. But first, I'm going to start with a story about lasagna. So I'm not a professional cook. I'm not even really an amateur cook. I'm just someone who's trying to teach himself how to cook. And one day, on a frigid New York winter, I decided to try my hand at making some lasagna because it would be warm and cheesy and delightful. So I started looking up some recipes online. I went to allrecipes.com, and I found one. And it looked pretty good. 4.5 stars, 35 reviews, one particularly good review, and I'm like, okay, I'll try my hand at this. It doesn't seem too hard. So I started reading through the recipe, and I was like, okay, only 30 minutes of prep, that's not so bad. Brown sausage and ground beef with onion and garlic in a large Dutch oven or heavy pot over medium heat, cooking and stirring until meat is fully cooked through 10 to 15 minutes. Oh my God, I'm already so overwhelmed and stressed out by this. For some reason, my brain just doesn't parse full paragraphs of text like this very well. And reading a recipe like this makes me really stressed out. I start worrying, is there a concrete order of this process? Do the bullets actually mean anything? Are there steps within the paragraphs that I'm missing? Which of these processes can be parallelized? I'm not really sure. And then, I can't really, let's say I'm in the middle of cooking, I'm stirring the sauce or whatever, and I want to take a glance and figure out how much parsley I need to put in the middle of it. I don't know how much parsley I have to dig through this wall of text. And then there's weirdnesses with the ingredients, both crushed tomatoes and Italian-style crushed tomatoes. Fruits.com doesn't even have an option for that. So I'm really lost here. In short, I find that there's a lot of data points buried in this paragraph, right? And buried further within this bulleted list. So really what I'm here to do is complain about bad syntax, I guess. Specifically the syntax of natural languages. The problem with cooking recipes is that there really isn't an alternative to natural languages when it comes to writing them. One hasn't been invented. And natural languages are very noisy. One might say that natural languages are the noisiest programming languages, right? So I figured we need an alternative. I guess one could say I got a case of programmer brain when a really hard and interesting problem prevents you from functioning like a normal human being and just cooking the lasagna, right? Okay, so let's take a step back, though. I don't want to start off with lasagna because it's a pretty complicated recipe. So to see how I approach this problem, let's start with something simpler. So this is Noah's New York breakfast. Like I said, I'm from New York. I like talking about it a lot. And this is a pretty simple recipe. You take a bagel, you cut it in half, you toast both halves, you let it sit, put on some cream cheese, some lox, smoked salmon, in other words, and an onion, and then bam. You got yourself Noah's New York breakfast, right? Okay, so this is already a bit better. I can see the amounts are, the ingredients are listed ahead of time. I can do my mise en place. I know a little bit of French. There's the paragraphs aren't as long, so I can kind of parse this out a little bit. But I still don't have a concrete ordering of things. I'm more of a visual learner. So something like this would look a little bit better to me. This is really great. Now I can see, the ingredients are visually distinct from the techniques that you're applying to them, right? I can see the amounts very clearly, 2 ounces of cream cheese, 1 slice of Vidalia onion, and I can parallelize the processes. This is really awesome. Flowcharts. Oh, you guys are going to like this talk. Okay, so it's easy to see what order things come in and break it down. And for visual learners, this is a lot better. Obviously, I can't convince everyone to think this way. A lot of people would prefer the paragraphs. This is limiting just as much as the previous example was. But let's go even further. This is Ruby. How many people have experience with Ruby? Okay. There's a lot of Ruby Elm devs. I think that's pretty cool. So this is even better for me, actually. So what do you got here? You got it's very expressive. Ruby is always very expressive. Your data points are separated and distinct. I can see up at the top exactly how many quantities of everything I want. The order is extremely clear because it's a procedural program. So that's all really cool. But there's some pitfalls to this. First of all, I have to like assign all my ingredients. Oop, mic just went off. That's okay. I'll keep projecting. I have to assign all the ingredients ahead of time, and I don't actually have to use them all in the recipe. So I had them all listed at the top, but there's no guarantee that I'm going to use them all. Nothing prevents me from smearing an onion or something like that. I don't know, toasting the cream cheese, right? And I really can't tell what I can do to what, right? If I could call, cream cheese.toast, and oop, there it goes. Thanks, guys. And nothing would happen, right? So it's very expressive, and there are a lot of steps taken to serve the expressiveness. But I can't really see the shape of anything, if that makes sense. So it reads like English, but I don't actually know what operations I can perform on what. So I was like, you know what? I can do this better with Elm. So needless to say, I never got around to making the lasagna, did I? Whoop! Uh-oh. Okay, that was fun. But something beautiful was born of my laziness and general difficulty, because instead of making the lasagna, I wrote this talk proposal. And then the next day, I started sketching out a lasagna recipe in Elm. One thing I noticed is that I didn't get very far before I had to undertake substantial refactors. And the reason for that is I started approaching it as one would approach a recipe written in Ruby, which is starting with expressiveness and then figuring out the rest after, right? You design the interface, and then you design the implementation details. Elm doesn't really want you to do that. Elm wants you to model the problem first, right? So I had to start thinking, what exactly is a recipe, right? And currently, the way most recipes are written, they're just strings. Sometimes they're structured strings, sometimes they're structured into, there it goes again. Sometimes they're structured into HTML documents, or ordered lists, or paragraphs, but really they're just strings. Someone's just writing them on a piece of paper, or maybe printing them. And that's cool. I mean, strings are really cool. Strings are infinitely expressible in a way, right? All modern literature is written with strings. But representing something as a string is limiting to all of us in ways that feel really intuitive, right? Because we're relying on humans to be able to process that information. And there's no inherent meaning to the string itself. It just means whatever it means to someone. If someone wanted a flowchart representation of a string recipe, we'd have to build a natural language processor in order to do that, right? And that would be a really cool subject for a talk, but that's not what my talk is about. My talk is about something, I think, a little more relevant. So modeling the recipe problem helped me develop a better vocabulary for talking about the advantages of type systems. And that's sort of what I want to get at here. But to do that, again, we have to scale it back a little bit, because I don't want to talk about the full recipe first. And instead, I'm going to talk about one piece of the recipe, which is the amount, right? For example, 2 ounces of cream cheese, right? So again, you could express an amount as a string, and in fact, I started off by doing that when I started writing this domain-specific language. You would just call the ingredient function, and you would hand it a string, and that would be your ingredient, just 2 ounces of Philadelphia cream cheese. But there's only one way to interpret that, right? If I wanted to translate ounces into some other measure of volume or weight, I couldn't really do that with a string, again, unless I built a natural language processor. The lack of structure in this representation makes it really hard to identify the data points in the way that I originally wanted to when I was looking at that long recipe. So I ended up with something that looked a little bit more like this. There's a function, ounces, that takes the integer 2 and constructs some data out of it. So I added some constructors to my data type and eventually came up with something like this, which has a lot more options for what your data can be, right? It's not just a string. And just by looking at the type signature, you know a lot more about what this data represents and how to extract the relevant information that you want from it. The words pinch and dash actually mean something to chefs. They're not just there for an added bit of zest. Zest probably also means something. You can have a number of things, you can have a weight of things, you can have a volume of things, you can have a fraction of things, which is represented by a float. And the point is that just by looking at this type definition and seeing it applied to different things in the code, you know about the shape of what you're dealing with, right? Another benefit is that impossible states are now forbidden. You can't have a qubit of cream cheese, right? Or some other nonsense word. And as an added benefit on top of that, we get to constrain the type size of this amounts, which I'll get to in a second. So the point of all this is that types provide structure to your data, which we all know. But the bigger point is that structure provides meaning to your data. And I'm not just talking about the meaning that one would get from, say, reading Moby Dick, but inherent meaning that's inherent to the type. So a good example of this is Boolean, which is, I think, the most meaningful type, the type that most encapsulates its own meaning, right? The word Boolean means something that can have two values, essentially, right? And what is the type Boolean? It's true or false. And of course, the words true or false, we interpret and take them to mean what we will. But at its essence, this is what a Boolean is. And you look at this type signature, and you instantly know what it is and what it can be used for. So let's talk about this idea of type size for a second, because I think this is also a useful piece of that vocabulary of discussing types and improving programs. So there's a developer named AlelDev. She's Queer Types on Twitter. And she wrote a really fantastic blog post about type size that I forgot to put the link in here, but if you Google it, you'll find it. Every type has a size. A Boolean has a type size of 2 because it can represent 2 values. A string, in practice, has an infinite type size. It's limited by memory, but in practice it's infinite, and there are an infinite number of permutations of what a string can represent, right? So just to go through, if you'll indulge me with a brief exercise, if you had a type called flag colors, which had 3 constructors, red, white, and blue, applies to both France and the United States. That would have a type size of 3, right? There's three possible constructors. If you add in some union types, you follow the order of operations, you multiply through the union types, and then you add the sum types. So Boolean has two possible values, flag colors has 3. On the left side you get 6, on the right side you get 1. You come out with a type size of 7. And finally, you just wrap that thing in a maybe. That just adds the nothing on the right side, so you come out with a type size of 8. And this is a really useful concept and exercise to do with your own code. Because really what you want to do is make the types at the core of your program as small as possible. This will make your programs a lot more resilient. And as a room full of Elm developers, we all already know this, more or less. Because when we go to define our update function, we generally don't switch on a string. We switch on a union type, which has a constrained number of values. And actually, yesterday at the workshops, when I was going through Richard Feldman's, I don't know where Richard is, but his workshops with someone who was completely new to Elm, and we got to the part where you replace all of your string messages with a union type, it like clicked, right? Of course this is more resilient. It's super intuitive once you go through it yourself. But developing this vocabulary for talking about it allows you to apply it to other areas of your program, right? So coming back to my bagel recipe, this looks pretty similar to what we had before. The difference is that this is generated by Elm code. So here's a really basic example of using the DSL that I built. By the way, this is not really intended to be useful, but this was a fun exercise for me to do. And so the library is called Cookbook. It exposes all these technique functions for applying techniques in the way we saw in the flowcharts, and then all these amount functions and functions for building ingredients and things like that. But I'll just draw your attention to 3 parts of this real quick. One is this part right here, where we encode an amount, a quarter of a pound. And I think this is really cool because this is just as expressive, if not as more expressive, as the Ruby code we saw earlier. Ruby is touted as like the most expressive of all programming languages, but this is pretty much the same thing, and we don't have to monkey patch the float class in order to get it, right? Okay. The second thing I want to point out is the use of function application here, or what some Elm developers at the New York Elm meetup call write pizzas. This is a really, really nice way to build Elm programs, or to generally build up data types that are inherently composable or applicable to each other. The key point here is that all of the steps in the process have to share a type. And when all the steps share a type, you can define composition and application functions for them. In this case, the techniques are application functions. And then you can apply them in this way. And they become joined together, right? And it reads really nicely. It reads like procedurally and in the way I would want it to read. And the last thing I want to point out is this generate HTML function. So bagel right there you can see as the type recipe. Generate HTML takes the type recipe and generates HTML, right? Very simple. But there's no reason why that couldn't say generate markdown or lag, or generate flowchart, or generate anything else, picture graph, whatever, however you want to read your recipe, right? You can write an interpreter for it. So long as the library exposes a way to get at the values within that data type, you can write an interpreter for it. So there are limitless interpretive possibilities here. And it doesn't really matter how you want to interpret it, because we have a standard data format now, and this can be used by any interpreter to produce any kind of content. And the thing that allows for those kinds of interpretations to be easily applied is the structure of the data, which is shaped by the type signature, right? Okay, so returning to this question, what is a recipe? So the reason why I chose Elm to do this is because Elm is really good at modeling abstract stuff as data, and the type system just, I like it a lot, obviously. So what is a recipe? I had to consider some questions, like what are the actual qualities of a recipe? Well, it's a big list of ordered instructions, right? Each instruction involves some number of other components or ingredients and produces a new component. An instruction can involve some duration and some temperature, unlike the ingredient, which involves some amount. Each ingredient has an associated quantity. And finally, the instructions form a kind of weird directed graph and not exactly a list or a tree, because they can break off and be recombined, right? So then I got to thinking, okay, how can I take these qualities and make a type out of them, right? What do I need to consider? Well, I talked about type size earlier, and it turns out that our recipe type does have to have infinite size. And the reason it has infinite size is because you can keep tacking things onto the end of it or changing things in the middle of it, right? So that there are an infinite number of permutations of the values that the recipe can represent. But it also needs a constrained structure. This is lagging a bunch. It also needs a constrained structure and a meaningful structure, something that's going to give it the inherent meaning I was talking about before. And my model for what that should be like is a list, right? When I say I'm going to use a list to any other programmer in the world, except one that maybe speaks a different language, they're going to know what I mean. They're going to know what a list is. They're going to know what operations can be applied to it. They're going to know how it's structured. It has meaning, the data type itself. And a list is infinitely recursive, which has an infinite type size. So that's exactly what I need. Here's the type signature for list, for those of you who aren't familiar with it. Type list A equals empty or cons A list A. This is how it's implemented in Haskell as far as I know. I don't know about Elm. But you can see how it's a recursive type because it references itself there. So I needed something similar for my recipe. And this is what I came up with. Now, this isn't optimized in any way. But the point is that you look at this, and you know exactly what a recipe is immediately. You know that a recipe can be an ingredient or a step, but that they're fundamentally the same thing. You know that it has associated amounts. You know that if it's going to be a step, it's going to have some reference to another list of recipes that live somewhere else, or it could be one recipe that points at another recipe. But either way, it has some knowledge of what came before it, right? There's a sequence of steps going on here. And then you have the name and instruction, which are both still strings, because there needs to be some amount of human interpretation in there. So the point is that strings are okay to use so long as the thing that you're using it for is meant to be interpretable by humans, I think. Now, this doesn't have a small type size. This has an infinite type size, in fact. But if you want to build something with a small type size or something that's very simple, you actually don't want to use a string. Strings seem very simple, but they're actually extremely complex because they have infinite permutations, right? So going back to the slide earlier, always prefer small type sizes to big ones. Another cool thing is that you look at this type signature, and aside from the names, recipe, and ingredient, you realize that this actually has nothing to do with cooking. So we saw in Evan's presentation earlier that he started with something called fruit list and ended up with something called bounded set, right? When you look at the type signatures, you realize that you're naming things often according to the context that you're using them in. But you could easily see how this type could be used to represent something like this. It's just an order of steps with some amount of base ingredients, right? That produces an awesome X-wing. Or something like this, which might look familiar to some of you. it's just you start with a list of ingredients, and eventually you have a shelf at the end, rather than a lasagna. I don't know which you prefer. I prefer the lasagna. Back to lasagna. And I'm actually kind of thankful that my talk was pushed until after lunch, because this isn't making any of you hungry now. This is the recipe that I ended up with, written in Elm. Feel free to take a look at the different parts of it. I'll point out a few of them, and I'll also share these slides later in the Slack channel or something like that. But one thing that's cool about it, each different function is, can be taken and used somewhere else, right? I could export sauce mix from this module and use it in a pasta recipe, right? Everything's inherently composable in that way. I think it's extremely expressive. You can read it pretty much as you would read English. And finally, if you look at the type signatures, if you actually examine the recipe type, you would be able to derive a whole lot of meaning just from those types. And this is the HTML that recipe produces, which, reads like a recipe, more or less. Again, I'll post these later. In the end, I don't think anyone's actually going to use this software. I'm totally violating the principles of Greg's talk in that I didn't user test this on anyone, and I just kind of did it because I thought it would be fun. And it was fun, and I learned a lot from it. So in that way, it was a good exercise, and now I get to share that with all of you. So what do we get from this? What could we get if we extended this functionality and if people were interested? And well, this is part of it that I already built, which is JSON encoders and decoders, right? It's actually super easy to encode and decode recursive types. So you can encode this to JSON and send it to a friend, and they can decode it and use whatever software they want to interpret it. And then if they're a French speaker, they can read it in French, and then if they like flowcharts, they can read it in a flowchart or whatever. We can also define different interpreters ourselves. This is really cool. This came up at the New York Elm meetup. Because it's a recursive type that can detect all the ingredients involved, you could have rule sets for what you want to eat and what you don't want to eat, which lots of people tend to have, and define them like this. You could define a type diet. It's like vegetarian or kosher or halal or paleo or whatever you are. And then you could add that to the ingredient type, a list of diets that this satisfies. So if pork is in your dish, you could immediately detect that this is not vegetarian, kosher, or halal, but it is paleo. And finally, this is machine readable, which is super cool, because that means that one day when we build robot chefs, we won't have to make our own lasagna, and we can just let the robot do it for us and write code instead, which would be pretty cool. So yeah, that's all I got. Thank you for listening, and yeah.